examples of molecular simulation is performed. We co-authors are Krzysztof Hałagan, Rafał Kielbik, Jung, where research was conducted at the Department of Molecular Physics and the Institute of Physics of the Lodz University of Technology. In my research, I deal with simulation of complex fluids. By complex fluid, we mean fluids containing an additional of a low molecular weight solvent, also very complex macromoleculars. For example, polymers. By polymers, we mean macromoleculars that are composed of many, sometimes even thousands or tens and thousands of such repeating monomeric units in a linear arrangement with a more complex topology, such as star or brushes. We problem with simulation is this type of system is that way involve a very large variety of space and time scales depending on the phenomenon we want to study. Such a simulation is demanding in terms of hardware. We need dynamics because we are interested in the dynamics of such systems. We want to have atomic or almost atomic resolution. The device that I am presenting today operates very well in this area with order of magnitude of theoretically available to ARUZ. In the area that I showed in the scope of scales, time, distance, the algorithm of cooperative dynamics. The dynamic lattice liquid was developed. It was developed by Mr. Tadeusz Makuła. Movement as such a system can be said to be of two types. Translation of movement over a longer distance and oscillation of a given object and a result of caging effect for neighbors. One time step involves the completion of several stages. Drawing those direction vectors that correspond to the motion test, we can create new bonds, other probability tests related to other interactions. We search for cooperative groups. We check the integrity of bonds. We move along accepted loops. You can see lines connected additionally by the bond. We execute such loops that would cause as a consequence ranking of bonds. Loops that are allowed 5 each particle moves by one in accordance with the vector. We change the mass of this macromolecular grows. The last macromolecule is active. It can attach more to itself. This chain grows over time. The problem is that the probability of this attachment is too high when we get, for example, to maxima in the mass distribution. Despite stopping the reaction, the next node, the mass of the polymer still grows. The more complex the shape of these chains, the longer the simulation times become. Unfortunately, we need long time scales, 10 to 9, even 10 to 10. 1 time step per second is simulating 43 nanoseconds for real time per day. Classical MD has 3 orders of magnitude smaller time step. Single threaded LL is about 20 cycles per second without bonds. 10 to 9 is equal to 1 millisecond of real time. Multi-threaded DLL is about 100 cycles per second without bonds. Supercomputer, okay. Giant network, but communication between nodes is the performance killer. Algorithm execution is very slow. GPU, cards, cluster construction, difficulties, lack, cost. The slides show a supercomputer in Quebec, Canada. Almost 16,000 CPU units of half of supercomputer was used, 100 cycles per second. The resulting file will be very large, 40 terabytes per file. We used a 32-core Threadripper. How does the number look, which appearance in the form of million? But still 80 cycles per second maximum. On NVIDIA, we managed to get 1,012 cycles per second. Unfortunately, a huge cost for availability. An idea appeared. Let's build a dedicated device. We treat a persistent in an algorithm of a network as a single data processing element. Let's combine this data into a three-dimensional grid. Let's describe it using logic gates. We'll throw it into FPGA. FPGAs into printed circuit boards. Connect large number of hosts. History. The idea, late 90s to 2005. In 2008, a microDLL was created. In 2012, MDLL was created. In 2015, ARUZ was created. FPGAs are attached to a PCB based on a 49 laminates. One FPGAs act as a master which manages communication synchronization or 8 slave FPGAs within on board. Slave systems are in fact devices that are responsible for logical operation. 54 RJ45 network sockets are soldered to PCB. These sockets are responsible for communication of even PCB with other PCBs. ARUZ built in BioNanoPark in Łódź. 12 columns mounted vertically form a well-colored panel. 20 panels in total. A cylinder-shaped structure with a height of 5 meters and a diameter of 14 meters. Controlled by 2 main servers and 20 computers. Each computer is assigned to one panel. Power continuity is ensured by an emergency gas power supply. Dedicated power supplies. Here is the logic of connection between panels. This is the so-called frog jump method. It is also used in supercomputer. In the future, we plan to use this machine, for example, to simulate optoelectronic system. We are currently working on machine learning and neural networks application. Let's show successful application in the field of molecular modeling of complex systems. Here we see polymer stars, occur and chains attached to it. Here the system differ in the number and length of arms, but also in concentration. These are simulation boxes. Simulation boxes. In the driving were slow for simplicity, only the polymer itself without the solvent. Experiments. Here we see images from an electron microscope compared to geometry from our simulation. The graph shows how we correlated the solvent relaxation time with star density. It turned out that the cluster to the star's core. The movement of this solvent is much slower when that which is more outside. Another analysis system, polymer brushes. This time linear chains attached to the surface, where the two brushes in front to each other. The studied system with various guiding density and length dp of chains. Different colors were used for both layers. The shape of the individual chains was analyzed. The chains were different lengths. They were drawn by polymerization. The short chains were coiled. The longest one had from or such unfolded flowers by impact of opposing brush. We also studied the dynamics of the solvent. In the images, the red colors indicates the movement of the solvent, which is not disturbed. The darker the color, the less mobile the movement becomes. It also depends on the length of the chain. If brushes are separated, then a free movement region is visible. If we analyze the mean square displacement, then of different time scales diffusion is not always normal diffusion. subdiffusion is present. The effect is two minims. The slowdown effect occurred twice. Battle brush shapes. The influence of the length of side chains on how the dynamics of such a brush changes was analyzed. The result was then compared with the experiment MMA methyl metacrylamide P poly in monomer medium. Comparison of LG the size simulation by ARUZ simulated the classical MD and from the experiment. The results are superimposed. Left figure simulation cover the entire area. The right figure shows how fast the chains moved the MD experiment. Experimental results don't always overlap. Experiment is difficult. Static masses on the left and dynamics diffusion on the right were analyzed and confronted with experimental data. Again, a very nice data overlapping was observed, confirming simulation usefulness. There was no polymer here, but we allowed ourselves to introduce vacancies into the system. Then we have such a variant of the DLL algorithm when, in addition to such envelope loops, we also have movement using empty points. Result agreed with Rosenfeld theory for liquid. Simple chemical reaction. Here is an example of such a reaction performed by us in the laboratory. This reaction is called saponification. It has second order kinetics. The simulation results were compared with the result of the experiment for this particular reaction and with the theory with the solution of differential equation. As you can see graph on the right, all the points lead up to this one such curve, which means that the energy to reproduce this reaction with second order kinetics. Experimental data were downloaded from Johns Hopkins University regarding the numbers on infected people tested in Poland in the period from October 1st, 2020 to November 15, 2020. If we assume mean infection time, K1, as 5.88 days and the transmission rate K2 as 0.26 per population per day, when obtained data fits perfectly. We prove when a chemical reaction model can be used for epidemic modeling. Gray region do not match change of dynamics, openings of shopping centers in Poland. Movement in three different polymer systems was studied. PM was a regular three-dimensional polymer network chains previously defined in space. Mesh CISA here 3 and 11. The network was stationary. SPM irregular network, high randomness of the network's shape and large difference in the local polymer density in the system, regardless of the average mass CISA. We see the value of the reduced solvent self-diffusion coefficient of the latest system as a function of the polymer concentration. The value of the diffusion coefficient is almost independent of the number of arms, while the rate of decrease of the self-diffusion coefficient with the polymer's concentration is higher for the cubic network TM. Additionally, the same relationship is present but as a function of the mass sheet size. Solvent mobility profiles. Reduce mobility of solvent movement compared to a system consisting only for solvent in regular PM networks. Irregular SPM network represent a large cluster of points with significantly limited movement consistency of slower polymer units and slower moleculars.